deals with span, issues of linear independence for a set of vectors, and a special way of checking whether differentiable functions are considered linearly independent or not, what a basis is, and then what coordinates are relative to some basis. So how would you articulate the definition of the span of a set of vectors? So if you have, say, one vector, or multiple vectors. What's the correct way to articulate the definition? Anybody want to risk it? The span of a set of vectors is?
Volume.
Huh?
Volume.
No, it's not volume.
Sure it is. In 3D space.
No, it's not a number. Okay? It's a set. It's the set of all possible linear combinations. So, if you were to, in principle, try to create the span of vectors, you would multiply each vector by some number, right? Scale each vector, and then add. It's a linear combination. Right, where these coefficients are a near field, or in our case, our scalar field is the real numbers. So it's the span is the set of all possible linear combinations for that set of vectors. So, for example, what would the span of a single vector be? Well, it's just all multiples of that vector, correct? And geometrically, what would this be? If, let's say, you have this Euclidean vector v1, and you create a span of this vector, so it's all multiples of that vector, you would get a line, correct? And will I necessarily get a line? What's the one case where the span of a particular vector does not give you a line?
Zero vector.
Yeah, if you happen to have the zero vectors. But that's the exception. So the span of two vectors that's the set of all possible linear combinations of those vectors, where C1 and C2 are real numbers. All right. And so geometrically, if these are V1 and V2 are Euclidean vectors, what are the possible things we could get? Like geometric objects. There's the silly case where both of these are zero vectors, right? Which would give in the case we just get a point. We'll just get the zero vector. There's another case where V1 and V2, maybe they're not zero vectors, but they align. And so the span of these two vectors is still going to create a line. Or the third possibility is that V1 and V2 are pointing in independent directions. In which case the span of those two vectors is going to generate, it's going to bloom and generate a plane, two-dimensional object. Okay. So now, knowing what a span is, at least the definition of it, right, we can start asking questions like, is this particular vector in the span of this set of vectors? There's a vector in the span of, so for example, if I have my set of vectors, let's say V1, I'm just going to label that, and V2. And it's a pretty simple example, but so this is a set of two vectors, right? And the question is, call this maybe W or something. Is the vector, say U, in the span span of that set of vectors. Well, what does it mean for this vector to be in the span? Well, since the span of these two vectors is the set of all possible linear combinations, for you to be in the span of these two vectors, there must exist some linear combination of these guys that give you this vector, right? So that suggests how to set up the problem. And that's the question, is U in the span of these two vectors? Well, if U is in the span, then we know that we can express U as some linear combination of V1 and V2. So here I'm not claiming that this is true. I'm saying that I'm really asking the question, is it possible to write U as a linear combination of these two vectors? So we know that we can interpret this as the matrix whose columns are these two vectors times the unknowns is equal to this vector. You can also see this by actually multiplying this out here. You get C1 plus C2 must be 1, and the 0 times C1 minus C2 must be 1, and then 1 times C1 plus 2 times C2 is 0. Right, and this is a system of equations, and this is just the augmented matrix. I'm sorry, this is just the matrix of coefficients, and this is the right-hand side of that system. And of course, we would solve this system by creating an augmented matrix. Here's the right-hand side, and we start row reducing. And we do that, you apply row operations, and you get, let's say, 1, 0, 0. In there. That's after row reducing. Yeah, this is the that's my matrix A. This is my reduced row echelon form of the matrix. Okay, so this tells me that, I read off the solutions, and this tells me that C1 is equal to 2 and C2 is negative 1. So indeed, we can check. That is C1 is equal to 2 and C1 is equal to negative 1. And we check, yes indeed, yeah, this vector is a combination of those. And these are just the coefficients in that linear combination. And we, if you like, coordinates. How would I check that if you have, let's say, two different sets of vectors, how do we check whether they span the same space? How could we do that? So we have, let's say, set W. So this is a new example. Set V. And I want to know whether the span of W is equivalent to the span of V. Question. So how would we go about trying to check whether indeed this is true? Well, if you take any vector in the span of W, right, you know that you can express it as a linear combination of these two vectors by definition, because everything in the span is some linear combination of those two vectors. So, and we want to see whether we can take that vector from W and also express it as a linear combination of vectors in V. and vice versa, right? So is it possible that if I choose arbitrary, say arbitrary linear combination of the vectors in W, is it possible to express it as a linear combination of the vectors in V? And if we are able to find coefficients, right? So for every A, B, we can find C and D and vice versa. Then we know that these two sets generate the same space. They span the same space. And probably the maybe clever thing to do, perhaps, is to bring everything to one side. So I'll just bring everything to one side. We get I'm going to do this. I'm going to, instead of writing the negative in front, I'll distribute it through to the back vector. I'll scale the vector by -1. And on the right-hand side, I will be left with the 0 vector. And we can try to solve for, see whether there are solutions for A, B, C, and D. And we do that by creating this matrix equation. And these are columns, the vectors become columns. And then you have your coefficients, A, B, C, D. And of course, this is a homogeneous system, right, inside of zeros. And we would augment this matrix coefficients here with the right-hand side. And, I mean, it's 0, so it's silly to write. And row reduce. Let me just see what row reduces to. That's a 3 by 4. That's right.
He's right past it.
So after I reduce, we get the following reduced row echelon form, the matrix. So what does that tell me? How do I interpret the results? Well, first of all, in this system, which case are we dealing with? No solution, one solution, or infinitely many? So we know that there are solutions, and that's all that matters, right? There's no in fact, what can we? It's a parametrized solution. So suppose that this is C, D. How would we define A and B in terms of C and D? Well, we see that A would be negative C minus 2B, and B is 2C plus 11. So given any linear combination in B, defined by these coefficients, we can always find A and B that would make these two equal. And vice versa, right? I mean, we could always solve for C and D in terms of A and B. So these two sets indeed span the same space, even though, so just because these two sets span the same space doesn't mean that these two sets are exactly the same, right? They're not equal sets because they have different vectors. But they still generate the same space. Okay. Now let's look at a more general question. Let's do a quick example of seeing whether a set of vectors spans, let's say, R3. So, given this set of vectors, you probably already know the answer looking at your notes. So the question is, does the set V, the set of vectors V, span all of R3? So how do you interpret that question? Well, to say that V spans R3 says that the span of V is all of R3. It's equal to R3. It gives you the whole three-dimensional space, right? So this means that if you take any vector in R3, you should be able to express it as a combination of these three vectors. So is it possible? Well, so let's do this. So take an arbitrary vector, so with arbitrary entries in R3. And then we want to know, again, we're almost rephrasing the question, is can this equal some combination of these three vectors? And then we get a matrix equation. So, all right. So how can we check whether we can always, for any x, y, z, we can always find these coefficients, right? If we can always define a, b, and c, regardless of what these are, then we know that every vector in R3 can be expressed as a linear combination of the three vectors. So those three vectors would indeed span R3. So probably augment the matrix here with the right-hand side. And start row reconciling. So, and of course, I gotta carry the row operation through, including the last column, through the last column. So here I would have z minus x. And then I'll just use this to zero these guys out. I guess we can almost stop here, right? Because what's the problem? What's the problem? It's this bottom row, right? Because we know that we'll have infinitely many solutions if this number is 0. So if it happens that z minus x plus y is 0, then yeah, in that special case, in those special cases rather, we can express the vector as a linear combination of the three. But, of course, this doesn't have to equal to 0, right? It's possible. For example, the vector 0, 0, 1. Z, this would be equal to 1, and then we have no solutions. So this vector in R3 cannot be expressed as a linear combination of the three vectors because we have no solutions for coefficients. So this means that since not all vectors in R3 can be expressed as a linear combination, this set does not span all of R3. So the answer is no, because there are some cases where we have no solution for the coefficients. What would this look like if, let's see, can you change this? Yeah.
I have a question.
Yeah.
Can we look at those and see if they can be written as standard basis vectors and know the answer to them?
They can be written as standard basis vectors. What do you mean by that?
Like a linear combination of standard basis vectors?
Well, each of these can be expressed as a linear combination of standard basis vectors.
Oh, those can?
Yeah. So,
Oh, okay.
right, I mean, so that, I don't see how that,
Okay, so basically, okay, I got it.
yeah. It doesn't, that doesn't really help us determine. It's definitely, there's a relation, right, between the standard basis vectors and these guys.
Hey, Les, is there a whole lot easier way by taking a determinant to determine it
But,
does it does not equal zero?
absolutely, I didn't want to do that
Okay.
here because I would want to use the kind of the first principle definition
Okay.
approach. But it's true that if we have as many vectors as we have dimensions, so these are 3 vectors from R3, then it's easy enough to stick these vectors into a matrix and complete the determinant.
Right. And the determinant will equal zero, so therefore it does not span.
Right. Yeah, but that's not something you can do if you had, if I had, like, for example, 4 vectors in R3, because then you don't have a square matrix. So what would this look like if suppose we change this to a 1 really quickly and ask the same question? We would set up the problem the same way. This would be a 1. And then we get 0. And this would be okay. So we would get this, right? So I just changed one of the entries here. And now, of course, you notice that the determinant here is not 0. If you have this triangular matrix, you take the determinant, you get -1, it's not 0. So we know that these 3 vectors are going to span R3. But just the first principles, right, says we don't have a row of zeros, we know we have a unique solution. We're able to reduce this matrix to the identity if we wanted to. So we have a unique solution, but the point is that we have a solution. We could write, regardless of what x, y, z is thrown at us, we always have a solution for the coefficients a, b, c. So we can always write, a is x plus y times the first vector plus c, and according to that, c, I guess I should finish row reducing. Just to show this explicitly. I should already have it solved. It's awesome. So if you reduce it all the way down, you get the following. So I forgot to, over there, it's wrong, I forgot to reduce it. So this means that I should be able to write any vector in the following way. So that's A times the first vector plus B, C minus X, times the second vector plus C give me the arbitrary vector from R3 x, y, z, and you can check that that's true. But that's explicitly showing that regardless of what we have over here, we have coefficients for this linear combination. All right, so now we want to talk about the notion of linear independence. Okay, so if you have two vectors, what do you think we mean by linearly dependent vectors? If two vectors are linearly dependent, then what must be true? So you have two vectors, and they're linearly dependent. Then our notion of the name linearly dependent, that makes perfect sense because we just say they both lie on the same line, both of these vectors. So one is just a multiple of the other. Okay. And if you have three vectors, then how would you, what would you mean by the three vectors being linearly dependent? Well, kind of, the intuition says that, okay, if they're dependent, then we can already express one of these vectors as a combination, a linear combination of the others, right? So we can either express v1 as a combination of v2 and v3, or perhaps express v2 as a combination of the others for v3. And so on. So if you have a set of vectors, and you say that it's a linearly dependent set, this kind of intuitive notion would say that I can express. So this is a linearly dependent set of vectors, then we mean by that one of these vectors can be expressed as a linear combination of the others. Can be expressed as a combination of the others. And here we would exclude I. Now, so that's a nice kind of intuitive notion of dependent sets, right? Independent sets of vectors. And so if we say that a set of vectors is linearly independent, we mean that there's no way you can express one of these vectors as a combination of the others. And that's a good notion of a dependence and independence, linear dependence and independence, but it's not a good computational definition. Because how do you know which of these vectors? So if I have a vector, a set of vectors 1, 2, 3, -2, -4, -6, and then say 1, 0, 0, 0, 0, 1. Or just even just one. Okay, this is clearly a linearly dependent set of vectors, and why is that? What can we eyeball here? Well, the second vector is -2 times the first one, right? So we can express one of the vectors in terms of the others. If we'd like to complete the linear combination, I'll put a 0 here. So one of these vectors can be expressed as a linear combination of the other two. But is it possible to express this vector as a linear combination of these two? It's not possible. So the problem with this definition is that, yeah, if they're dependent, then we know we can express one of these vectors in terms of the others, but we don't know which one or which ones. So it's not a good definition to help us compute the answer to the questions, a set of vectors linearly independent or dependent. All right, so we would make the following observation. If I can express a vector as a linear combination of other vectors, and I bring everything to one side, and have 0 on the right-hand side. Here what we observe is that there's some combination of the three vectors that's equal to 0, where these coefficients are not all 0. That's the main observation. And also, the converse is true. If you know that there's some linear combination of these three vectors, I'm just using 3 for illustration's sake. And these coefficients are not all 0. Maybe some of them are, but they're not all 0. Then you know that you can, let's suppose C1 is not 0, right? Then you know you can solve for one of the vectors in terms of the others. You can divide by C1 because we assume it's not 0. So this shows that this demonstrates that idea that if you can find a linear combination of your vectors that's equal to 0, but where some of the coefficients are not, then you can always write one of the vectors as a combination of the others, a linear combination. Then that brings us to the computational definition of linear dependence and independence. Okay. So we say that the set of vectors is linearly independent if and only if the only solution to the equation, the homogeneous equation, is the trivial one. That is to say, all the coefficients have to be 0. So why do we emphasize that this is the only solution? Well, because clearly C1 equals 0, C2 equals 0, all the way through Cn equals 0. That's a solution, that's for sure. That'll work. That's always the solution to the homogeneous system, right? Homogeneous equation. But if there are no other solutions, so the trivial solution is that you need one solution, then there's no way you can express one of these vectors as a combination of the others. So we're going to use this as our computational definition for linear independence. Okay. On the other hand, if you can find if there exists a non-trivial solution to this equation, so that is to say, at least one of these coefficients is non-zero. Then we know that we can express one of the vectors as a combination of the other, so we have linear dependence. So that's just reviewing this definition. So you have questions like, is a set linearly dependent or independent? A set of vectors. Getting ahead of myself. Again, we are dealing with that special case where you have as many vectors as you have dimension. Yeah, these vectors are R3. So we could just complete the determinant, and if the determinant is 0, the answer is these are dependent. And if the determinant is anything other than 0, then we have linearly independent set of vectors. But formally, what would we do? Using the computational definition, we'd want to check whether if we set up this equation where we have combination of these vectors. And we set it equal to the 0 vector, so we have this homogeneous equation. And try to solve, and we solve for C1, C2, and C3. If the only solution we get is the trivial one, then we know we have linearly independent vectors. But if you get a non-trivial solution, at least one non-trivial solution, we have dependent vectors. So, write this as a matrix equation. And hopefully here you can see why taking the determinant would be sufficient, right, to answer the question. Because we know that if the determinant of this matrix is not 0, this matrix is invertible, therefore we only get the trivial solution. But if we take the determinant of this matrix is not 0, then this matrix is not invertible, therefore we're going to get infinitely many solutions. But we reduce and we get, here's about a hand, here's the augmented matrix, and I will reduce. Get 1, 0, 0, 0, 1, 0, 1, 2, 0, right? So this tells me we have infinitely many solutions for C1, C2, and C3. So among those infinitely many, we have solutions where some of the coefficients are not 0. Therefore, the answer here is no. This is not a linearly independent set of vectors. It's a dependent set of vectors. And if that's true, if this is a linearly dependent set of vectors, we should be able to write one of these vectors as a combination of the others. And I can actually read what that combination is. I can read such a linear combination off this matrix. This says that, that 1 times the first vector plus 2 times the second vector should give me the third vector. So let's check. So 1 times the first vector plus 2 times the second vector in the set. That equals, let's see, 0, 5, 3 plus 10 is 13. So indeed, right, I was able to explicitly show that I can write the third vector as a linear combination of those two. So linearly dependent vectors. Okay, so what would the situation look like if we did have a linearly independent set of vectors? So can I go ahead and change this up? So if we had a 1 over here, and we ask the same question, we would set it up the same way, right? We create this homogeneous equation, we solve for C1, C2, and C3 and see if we have only the trivial solutions or we have non-trivial solutions. And if I augment the matrix and row reduce, I get the following. Clearly, we already kind of know, anticipate that this means there's a unique solution and C1, C2, and C3 all have to be 0. So that's the trivial solution. Therefore, the answer is yes. These are linearly independent. This is a linearly independent set of vectors. Okay. Right. So what if we look at a different vector space? So suppose we look at P2. So this is the set of all polynomials of degree 2 or less. Quick question, will this set polynomials, will that span P2? So does this set span P2? Can I, that is to say, am I able to express every polynomial of degree 2 or less as a combination of these three things? And you better answer yes. Right? Because this is exactly a linear combination of these three things. So give me any polynomial of degree 2 or less, right? And I can express it as a linear combination of these three things. The coefficients are clearly A0, A1, and A2. So but you might make the problem more challenging and ask yourself, let's say, let's call it A. So do these, so do these three polynomials span P2? Well, of course, that is to ask, can we take any polynomial to be 2 or less and express it as some linear combination of these three polynomials? So if we take an arbitrary polynomial, P2, can we express it as a linear combination set? Well, we would multiply this out and you gather the constants, so you get C1 plus 3 times C3 must be equal to the constant on the other side, right? Two polynomials are equal if and only if the corresponding coefficients are equal. So it must be equal to A0. Then you gather the x terms, so we have minus C1 times x plus C2 times x. and that's 0. That should be equal to A1. I'm just comparing like terms, right? And then the x squared terms, so we get C2 times x squared plus C3 times x squared. That should be equal to A2. And that's a system of equations. And then we would, write that as a matrix equation and start row reducing and whatnot. So we can either augment the matrix here with the right-hand side, or we can repeat the determinant. We reduce this to a problem in Euclidean space. And what do you get? Just row reduce. Apparently you can. Anyway, we could reduce and then we get the identity matrix here. So we, regardless of what coefficients we have for our polynomial, we can always find the coefficients in this linear combination which give you the polynomial. So these vectors, these three polynomials stand with 2. Okay, would you know that these, now, what if we ask the question, are these 3 polynomials linearly independent? What would happen? Well, we would create a combination of the 3 polynomials, and we would set it equal to the 0 polynomial. And that's where just the coefficients are all 0, right? So that would be like 0 times 1, 0 times x. 0 times x squared. That's the 0 polynomial. So if we change the question to, is the set a linearly independent set of vectors? Then you could set this combination equal to the 0 vector and solve the system. But of course, we already know, because since we already showed this, if A0, A1, and A2 are all 0, what's the only solution for the coefficients? They must be 0. Or if you'd like to start all over again with the right-hand side being all 0, Remember, we're trying to solve for the coefficients to check whether the only solution is the trivial one or if there are some other solutions. So if you start row reducing, you would get this. So C1, C2, and C3 must all be 0, because that's our unique solution. So since that's the only solution to this equation, we know that the set of vectors is linearly independent. And is there another way to do this? Yeah, so I guess we should talk about the Wronskian. If you imagine the set of continuous functions, right? Can you imagine why that would be a vector space? Why that can be considered a vector space? Well, if you take two, just check the closure axioms, for example, for a vector space. If you take two differentiable functions and you add them, you get a differentiable function, right? So that set of differentiable functions is closed under addition. And if you take a differentiable function and you scale it by some amount, you still get something that's, you can take the derivative of. So it's closed under scaling. And the constant function 0 is differentiable and it's your 0 vector and so on. So the set of differentiable functions is a vector space. Scale, you can add, and all that good stuff. So if I have a set of functions, I could ask the question, is this set of functions linearly independent or dependent? Like you do if you've had exposure to differential equations. That's a big question, right? So suppose we have, let's start with, let's do 3. So you have 3 differentiable functions. So these are all differentiable. And you want to know whether they're linearly independent or dependent. Well, you would use this, the computational definition, and you would say, if I create some linear combination of these functions, and I set that equal to the 0 vector, so that's just the constant function 0, and I try to solve for C1, C2, C3, will I get only the trivial solution, or will I get non-trivial solutions? So we'll make the observation that we can differentiate both sides with respect to x. These are differentiable functions. So we differentiate. Of course, these are constants, so. And that's right-hand side is still 0, and we can even differentiate again. Why am I doing this? Well, because I'm going to get a system of 3 equations, 3 unknowns. I'm going to get a nice square system. And you can write this as a matrix equation. First order derivatives here, and the second order derivatives. And then you have your unknowns, which are the coefficients in our linear combination. And that's equal to the right-hand side, which is all zeros. So now, because we have a square matrix here, we can use this idea of determinant, right, to see whether we have only the trivial solution, all zeros, or we have non-trivial solutions. So if the determinant of this matrix is non-zero, then we have only the trivial solution, so we would have linear independence. So the determinant of this matrix is called the Wronskian. And let me write the following. So this would be Vronskin, say W, of F, G, and H. That would be the determinant of this matrix. And if the determinant is not 0, then we know that the only solution here we have is trivial 1. So these are, we can say that this set of functions is linearly independent. So we could have applied that to the, I mean, it's more interesting if you have stuff like on your homework, you have exponential functions that you want to check whether they're linearly dependent or independent. But we could have applied this idea to our example of, what were the polynomials? It's a little cheesy, but. So we were asking whether these three vectors were linearly independent, right? Or these three polynomials. But these are differentiable functions, so we could easily compute the Vronskin of them. So let's call this here. The Vronskin of these three differentiable functions. The determinant, and we simply write down the functions. And we differentiate again, the second order derivatives. And you compute the determinant there. Let's see, I think I did that. Somewhere. That? Oh well. Anyway, I'm just going to expand about, let's say, the third row. So using cofactor expansion. 0, then minus 2 times plus 2 times. So we're just using cofactor expansion to find this determinant. Notice it's going to be a function of x. Then we can combine the like terms. So
It's -4.
yeah, the determinant
Yeah.
and
It's just -4.
and -4. I don't know what I did, but okay, that's not 0. Okay. So by since this is not 0, we would have linearly independent vectors.
Of course, since the determinant is not 0, it's linearly
Independent.
Independent, okay.
So you have a similar problem here, I guess, except it's exponentials. All right. So now we go to the question of basis. So what's a basis for a vector space? Well, a basis is a set of vectors which must span your space, right? Number 1. So a basis for a vector space is a set of vectors, or set of elements, whatever, such that number 1, this set spans space, so you can write any vector in your space as a combination of these, a linear combination. And number two, it's a linearly independent set. So you can characterize this basis differently as well. It's equivalent. You can say that you can express any vector in V as a unique combination of these vectors. There's only one way to express each vector in terms of these. Then these must be linearly independent. So, but really, check if you want to know whether something's a basis, you check these two conditions. So for example, these three vectors, this set, that we called A before, spans P2, right? We showed that. So we showed that A spans P2, and we showed that A is a linearly independent set. So we can conclude that A is a basis for the set of polynomials of degree 2 or less.
You have to prove both, or just one?
Formally, you would prove both, right?
Okay.
Again, if you have special cases where you have as many vectors as you have like dimension or something, then prove one, even the other. But, so let's do something like this. Okay, consider a subspace of the skew symmetric matrices. So this is W is the set of all, say, 2 by 2 or 3 by 2 matrices, such that A transpose is equal to its negative. So that's a subspace of 3 by 3 matrices. And this being a subspace, maybe we can try to find a basis for this subspace. So how would you go about that? Well, you need a set of vectors which will give you all possible symmetric 3 by 3 matrices, and also are linearly independent. So what I can do is I can take a skew symmetric matrix that's 3 by 3. And it's arbitrary, so all I know is that this is like A, this is B, this is C. These have to be zeros. This would be the negative of A, correct? This would be the negative of B, and this would be the negative of C. It's skew symmetric. You transpose this thing and you get the negative of this side. So what can I do? Well, I can easily write this as a vector containing just, a matrix containing just the A's. Plus just the B's. And then of course you can factor out, like, think of this as scalar times this particular matrix. Well, what have we just shown? What we have shown is that any skew symmetric matrix that's 3 by 3 can be expressed as a linear combination of these 3 particular matrices, right? So, do these 3 matrices span W? Sure. Every skew symmetric matrix that's 3 by 3 can be expressed as a linear combination of these 3. So those three will definitely span W. But is that set of three matrices, is it linearly independent set? And you can show that it is, right? Because you would take this linear combination and set it equal to the zero matrix. Hope you don't mind. It'd be 0, 0. That's a skew symmetric matrix by default. It's transpose the sequence, so it's negative. So we're checking for linear independence. We have a linear combination set equal to 0 vector. And now we want to solve for A, B, and C. And I hope it's clear that the only way this will happen is if A, B, and C are all 0. So these three matrices are also linearly independent. So those three matrices will form a basis for the subspace W. I'm not going to write that out. I hope that makes sense. Okay. So what are coordinates, by the way? Well, if you have a vector space, and you have a basis for that vector space, by definition, this is a basis. And bases aren't unique, so I'm using the word A, not B, right? A basis. So this is vector space. This is a basis for that vector space. This means that I can, by definition of basis, this means I can take an arbitrary vector in our space and express it as a linear combination of the basis elements. Remember, the basis spans space. And these are the coefficients in that linear combination, correct? Those coefficients are known as the coordinates relative to the basis. So these coefficients, C1, C2, in this linear combination are the coordinates relative to the basis. Oops. So, since we are running out of time, I'll just do a kind of standard cheesy example, but okay. You can show that this set of vectors is a basis for R3. We have three linearly independent vectors, so it's going to span. So our vector space is R3. This is the basis for it. It's not your standard basis. All right, so now if I take a vector, let's say 3, 6, 3, 1. I ask you, what are the coordinates? So here's an arbitrary vector, or one I picked from R3. And your job is to find the coordinates of this vector relative to this non-standard basis. So it's called basis. Relative to basis B. Well, how would you find the coordinates? Well, you say, well, I know that coordinates are just the coefficients in the linear combination of the basis elements that give me the set vector. So there's some combination of the basis elements which have to give me 6, 3, 1. and you'd solve, and you would get a unique solution here, and then the solution would be that C1 is 3, C2 is 2, and C3 is 1. And these would be the coordinates for this vector relative to this basis. Of course, if you have, what would the coordinate vector be for this vector relative to the standard basis? The standard basis being the one that for R3 here, we're used to the elementary columns here, E1, E2, E3. What would the coordinates of that vector be?
6, 3, 1.
6, 3, 1, right? 6 times 3 times 1, yeah. So that's just to quickly illustrate that, you have the same vector, but because you're using different bases, you get different coordinates. Yeah. Different coordinate systems have different representations for points. Yeah. Okay, I think that's all I have unless you have questions.